Work done on a charge by an electric field. There are two primary questions for this video. What is required in order to move a charge in a field? And how can you make an electric field stronger? Alright, so let's go ahead and get started for this. There are going to be two practice problems that I'm going to leave you with for this video. I expect you to do both, or at least attempt both, for class. Alright, so for these two concepts that I'm going to talk about, for work done on a charge by an electric field as well as voltage for an electric field, I want to derive the equation for you so you can see where the equation comes from. So I'm going to use these series of questions to show that to you. Okay, and so what is the equation for an electric field? The equation that we have is E is equal to F over Q. Now what I want to do is I want to rearrange this a little bit. So it's going to be EQ is equal to the force. And what is the equation for work? This goes back to first term, and we have work is equal to the force times the distance. And again, I'm going to rearrange this. So I'm going to put this as work over distance is equal to the force. And so hopefully you can go ahead and see what I'm going to do. So how can we combine these two equations together? Well, since I've already isolated the force for both of these, I can set the two equal to each other, or you can think of it also as substitution. So it can be W over D is equal to EQ. And so what I want to do is I'm going to rearrange this so we get W is equal to EQD. And this is often written as W is equal to QED. But really these are the same. And that's your equation for the work done on a charge by an electric field. What you can tell from this is that this equation really isn't anything new. It's just a combination of two older equations. So this is your practice problem. How much work is required to move a 5.2 microcoulomb charge 0.23 meters through a uniform electric field of 752 newtons per coulomb? So give that a try, and we'll go back to that in class. So for the next part, this is about voltage. And again, I'm going to go through this series of questions to show you where we get the equation from. So what is the equation for work done on a charge by an electric field? We just figured that out. That is work is equal to QED. And then what is the equation for voltage? Voltage is equal to, that's going to be work per unit charge. So this is going to be work over Q. And hopefully you can go ahead and see what we're about to do. So how can we combine these two equations together? We have W equals QED and V equals W over Q. And so all we're going to do is substitute this work over here into here. So this is going to look like this. V is equal to QED over Q. And so since we have a Q on top and Q on the bottom, we can cancel out these two. So this equation becomes V is equal to ED. So the voltage is equal to the electric field times the distance between the two plates in most cases. The other way to think about this is if we look at the electric field more specifically, we can say the electric field is equal to the voltage over the distance. So depending on the voltage and depending on the distance will determine the electric field, or vice versa if you look at this equation. Both of these equations are the same. They're just a slightly different way of looking at the problem. Your practice problem for this is a spark jumps 2.54 centimeters from the point of a Tesla coil to the light bulb. If the Tesla coil can produce a voltage of 11,200 volts, what is the magnitude of the electric field?